Okay, so in the last video I basically talked about piecewise functions, and then I had like comments on here. Some of you had questions or requests that you had to make. So the first comment says, when excluding and including values, do we only look at the x values? No, we also look at the functions. Just that if we go on and look at my functions in that piecewise function, we end up with x plus 2, x squared, and minus x minus 2. All of these functions are continuous, so that's why I only decided to look at the intervals on those functions. So I'm gonna give an example answering this comment here. So the second comment says that give us more examples on absolute values. So yeah, we're gonna look at those. Remember, an absolute value can also be denoted as a piecewise function. So yeah, let's get to it. Answering the first comment there saying we only look at the interval. Okay, so let's say we have a piecewise function defined by something like this. So when we have a piecewise function defined by something like this, firstly let's look at the interval. Let's say we're looking for the domains of this function. So we first look at the interval. We go from -4 to 0. So we're going to write -4, and we have 0 there. And we also have a second interval 0 to 6. So we go from 0 until 6. So we're only working at -4. So we're only working between -4 and 6. So we already know that the domain should not extend that, right? Okay, so now this function is 1 over x plus 1. This function is undefined at -1 because we're not allowed to divide by 0. So if you plug in -1 here, you're going to get undefined. And is -1 in this interval? Yes, because we're going to find -1 somewhere here. That's where we'll find -1. So that means that when we are writing the domains, you'll have to exclude this -1 because -1 will give undefined here. Okay, then for the rest of 1 over x plus 1, in this interval it's defined except at -1. So we'll proceed to the second function. So we have a function inside the square root here. What do we know? We know that inside the square root we're not supposed to get a negative answer. This therefore implies that x squared minus 4x will have to be equal or greater than 0. And if you solve for x here, you'll realize you have something like this, and then you have a parabola sloping upwards. So you have something like this, having 0 and 4 as intercepts. You realize that it's negative between 0 and 4. So we only include the numbers between 0 and 4. But 0 and 4 should be in the domain because that's where it's 0. The square root of 0 is defined. So we have 0 here, and then we have 4 somewhere there. And remember, 0 and 4 should be included, but this region should not be included because that's where we get a negative, and we can't put a negative inside the square root. So we just plot all this together. So we have our domain will go from -4, and -4 is excluded, right? -4 is excluded. And -1 cannot be in the domain. So remember, you can just shade the regions to make it easier. On the interval that you're working on. Okay, so we have a region from -4 to -1 with -1 excluded, intersection -1 to 0, which is this interval here, and 0 is included. We can check here. And just because 0 is included here, you have to check if 0 gives this, but here you don't really need to worry about 0 here because 0 is excluded in this function as well. So for this one, for this parabola, for this equation inside the square root, 0 is not included, but it is included in here, so it will be part of the domain. So now we proceed up until 6. And 6 here, it clearly says that the domain must be less than 6, so 6 will not be included. So remember, I said it's this region, intersection this region, and we exclude this region, intersection 4, and 4 is included to 6. And 6 is excluded. So this will be the domain of that function. That's how you'll identify the domain of that function. But this is a complex problem, but I don't think they're going to ask something this deep, or this hard. But it's technically easy. Just identify for undefined and defined cases, and then just link them, and then that will be your domain. And now, similarly, you can just plot the things, and then you'll be able to determine the range from this. So let's sketch. So we're going to have our Cartesian plane, and this one is going to have an asymptote at -1, and we have something like that. So if we plug in 0 here, we'll have 1 over 1, so we'll have an intercept at 1. So and then our graph is just gonna approach the asymptote. It's gonna approach the asymptote, and then from here from the left side of the asymptote, then we're gonna have something like this up until -4. Plug in -4 there, you have some about -1/3, and that will be the end value, and it's excluded. Since -4 is excluded, so you plug in -4 here, you get -1/3, and that point will be excluded. So you'll have a function something like this, and then that's the first piece of the function. And then you draw the second portion of h at x. And remember, if you pay attention to the domain, you realize that we're going from 4 up until 6. So if you plug in 4 here, you get 0. And then that point will be included. So we'll have 0 here. We'll have 4 is to 0 here, proceeding all the way up until 6. If you plug in 6 here, you have 6 squared. That is 6 minus 4 by 6, which is 24. And then you have about 12. So you'll have like some sort of a graph like this, and it continues up until about the square root of 12, which is root 12, and then that's where you get 6, and that will be our function then. So what is the range of this function? So this function, let's see, it continues indefinitely on the negative side, and the uppermost negative value, it's minus 1/3. So y will go from negative infinity up until negative 1/3, and then with negative 1/3 excluded, and then it goes from there, it jumps to 0, and it continues up until root 12. But if you pay attention to this region, it continues indefinitely from the hyperbolic side, 1/x plus 1, because this is just going to approach infinity. So we have union 0, with 0 included here, to infinity, and that will be the range of that function. With the second portion, it's where we talk about absolute value in the second comment. So let's say we have like f of x defined by something called an absolute value of x. An absolute value of x is sort of like the square root of x squared. This is by definition, the absolute value of x is equal to the square root of x squared. So if we have the absolute value of -2, that will be the square root of -2 squared, and that will be -2 squared. The negative will just go away, and then you just have the square root of 4, which goes to 2. And the absolute value of 2 will just be the square root of 2 squared, which is just going to be root 4, and it's the same as 2. So basically, notice something. The absolute value just takes away the negative. You just have the same interval, and it just takes away the negative. So that means that the absolute value of x will be equals to, then you represent this on some sort of a piecewise function, will be equals to x if x equal or greater than 0. And the absolute value of x will be minus x if x is less than 0. So that's by definition of absolute value. For example, if you have the absolute value of x plus 6, you look for where this region is positive. If you set x plus 6 greater or equals to 0, you get that x equal or greater than -6. So this means that this will be defined by x plus 6 as long as x equal or greater than -6. And if you work vice versa, then you'll have minus into x plus 6 for as long as x is less than -6. So that will be the definition of absolute value. Remember, absolute value just takes away the negative, so you shouldn't get the absolute value of something being negative. So an absolute value function can be represented as some sort of a piecewise function. So that means that if we were to graph f of x being the absolute value of x, and I said the absolute value of x is something like this, then we can represent that on a sketch. We can sketch that. Let's see. If x is less than 0, this graph is defined by minus x. And we know the shape of minus x is something like this, and it continues indefinitely in that direction. And then, if x equal or greater than 0, we define that graph as x. So in the graph, the line y equals x is defined by something like this. So this will be a function y equals the absolute value of x. It's going to look something like this. And then, what about the absolute value of x plus 6? Okay. Going back to y equals the absolute value of x, so f of x equals the absolute value of x, you can see that here, since there were no restrictions offered here, you see that the domain is x is all sets of real numbers. But what about the range? You see that the minimum value you get here is 0. So y goes from 0, with 0 included, up until every positive value. Infinity goes, every positive value is included. So a minimum of 0 and all positive values. Then you can do the same process with this one, the absolute value of x plus 6. You can pause the video and check if like you can be able to sketch this one, y equals the absolute value of x plus 6, and identify the domain and the range of this function. So let's see. I already gave you an idea of what this function looks like. So you can represent this in some sort of like a piecewise function, and then you can graph from there. So we have our Cartesian plane. So for x less than minus 6, remember minus 6 is somewhere here. So we have minus 6 somewhere there. So for x less than minus 6, this graph is defined by minus into x plus 6. So it's going to be something like this. It's going to go in this direction. If you plug in minus 7 here, you have minus 7 plus 6, which is minus 1, and negative into negative 1 is going to be positive. That's why I say it's going to slope like this. And then for x equal or greater than minus 6, we have x plus 6. What does the graph of x plus 6 look like? So the graph of x plus 6 is going to look something like this. It's going to continue from here and then proceed like that, and then where x is 0, we pass through 6, and it's going to continue in that direction. So, see, the domain is still all sorts of real numbers, and the range, the minimum y value is 0, and it's included. So it goes from 0 to infinity, continues indefinitely in both directions. So that will be the absolute value of x plus 6. But we can further shift this graph and say we have something like the absolute value of x plus 6 minus 3. So if we have the absolute value of x plus 6 minus 3, then if we try to graph that function, let's see. For this function, it's easier to like first define this function as some sort of a piecewise. We know that the absolute value of x plus 6, let me just change this. I already did x plus 6. Let's say x minus 6 instead. So we know that the absolute value of x minus 6 will be equals to x minus 6 so long as x minus 6 greater than 0. So that means that we'll define the absolute value of x minus 6 as x minus 6 if x equal or greater than 6. So that means that this function will be defined by x minus 6 minus 3 for as long as x equal or greater than 6. And then you can do this for the negative region, and then it will be minus into x minus 6 minus 3 for as long as x is less than 6. So further proceeding here, we have we can simplify x minus 6 minus 3 is x minus 9, and then minus into x, then we have minus x, minus into minus 6, we have positive 6. Positive 6 minus 3, that's gonna be positive 3 for as long as x is less than 6. And then here we have x greater or equals to 6. So this will be a version of y simplified. So we went from this to write something like this because we're familiar with functions without absolute values, and that's what I did. Transform the absolute values into a piecewise function. And then from then we're gonna sorry for my sketch here. Then from then we just plot the graph. We define the graph as minus x plus 3 as long as x is less than 6, and we know that we get 6 somewhere here. So when we get 6 somewhere here, and we define this as minus x plus 3, so we know that if we plug in 6 here, we have minus 3. Then we have something like, we can predict it somewhere here. Minus 3, where the y value is, where the x value is 6. And then, what does the graph of minus x plus 3 look like? So it's going to slope upward, right? Then we have something like this. If you solve for the intercepts, you realize that if you plug in 3 here, you get 0. And then you proceed like that. And then if x is 0, you realize that you have 3 there. And it's going to go in that direction. X less than 6. It's in that direction. And the slope, this is just a straight line. We know how a straight line looks like. And then is defined as x minus 9 for as long as x equal or greater than 6. Plug in 6 here, you get 6 minus 9, and then you have minus 3. Then this one is now an equal sign. Then we can Since it's the same coordinate minus 3, then we can shade this region here that it's included. Or you can just draw the graph and avoid this dot here. And then you realize that this graph is going to slope upward like that. And if you solve for this intercept, you realize that you have x equals 9. Then if you substitute 9 here, you get the y value is 0. So you have your x-axis, your y-axis, and then you have something like that. So that will be the graph of the absolute value of x minus 6 minus 3. So what are the domain and the range? So the domain will just be all sets of real numbers. We can identify that every x value gives a defined output. And then the range this time, realize you have a minimum value of minus 3. So when you have a minimum value of minus 3, then we realize that we go from minus 3 and we go in the positive side. So up until infinity. So that will be the range of this function. So you can like practice this stuff. Basically, it's really simple. But let me test you a little bit. Try sketch y equals the absolute value of x squared minus 9, and identify the domain and the range of that. Okay, can you identify what the graph is going to look like? Okay, we know that by definition, the absolute value of x squared minus 9 will be equals to x squared minus 9 for as long as x squared minus 9 is equal or greater than 0. Then we know that the shape of this. You can like try to solve the inequality first, and then find the interval that you're working on. But okay, so you have your critical values to be minus 3 and 3. So you plug in a number between minus 3 and 3, which is 0. And if you plug in 0 here, you get a negative value. And then if you plug in a number less than minus 3, for example, minus 4, then you get a negative times negative, which is positive. And then you get a positive value. Plug in a number larger than 3, which is just 4. 4 plus 3, 4 minus 3, which is positive by positive, which gives you a positive answer. So you realize that you have something like this. That will be your positive regions. So as long as x is less or equals to minus 3, or x is greater or equals to 3, then that function will be defined by x squared minus 9. For the negative interval, you just distribute a negative. So what I'm saying is that the absolute value of x squared minus 9 will be equals to, you denote that as some sort of a piecewise function, x squared minus 9. And then for as long as x is less or equals to minus 3, or x equal or greater than 3. That will be this interval. And then you distribute a negative into x squared minus 9 for as long as x is between minus 3 and 3. That's because that's where we got a negative region. That's where we got a negative region. Okay, so then you can then sketch the graph. So the graph is going to look something like this. The graph is going to, let's see, so you have this, but you have 3 there, and you have minus 3 there. That's just our parabola, right? Initially, that parabola was going to look something like this. If it did not have the absolute values, it was going to look something like this. But now, since it has absolute values, then it's going to do something like this. It's going to do something like this. Notice, then you have 9 there. So basically, it's just that the absolute values kind of like reflect the negative region about the x-axis. Only reflect the negative region about the x-axis. So similarly, you can graph y equals the absolute value of sine x and stuff like that. But now, what is the domain and range of x squared minus 9, the absolute value of that? So the domain, we realize that it's all sets of real numbers since there were no restrictions offered. And then for the range, it's technically all positive values. It doesn't have a negative value. So for the ranges, y goes from 0 to infinity. So that will be the range of the absolute value of x squared minus 9. Thanks for watching. Don't forget to share and subscribe.